Hello. We want to continue our discussion of the normal curve, and in particular we want to continue this discussion as we start to move from standard z-scores, which involve a single person or a single data point being compared to the population, and we want to expand that a little further. To do that, it's important that we talk about some terms that we've used a little bit in the past, but maybe now it's time to remind ourselves of those. The first of these, let me get my glasses, is going to be remembering the difference between samples and populations. These are population averages and population deviations. We want to remind ourselves about samples as well. So recall for a moment, let's keep this over here, I'll touch this example in a second. A statistic is a sample measure. While a parameter is a population metric. And as we close out this section, this chapter, it's important that we keep a very straight sense of what is a population measure and what is a sample measure. So let's discuss this a little further. A population is a collection of everyone we're studying. And in times past I've mentioned that maybe a very interesting population for me might be all of my statistics students in Introstats ever. That would be the population. Anyone who's had me as a statistics professor for introductory statistics. A sample might be one of my classes. So this semester I have some online classes and face-to-face classes, so I might say this online class is one sample, this face-to-face class is another sample, and so on. And I could compare these samples to the overall population as a whole and say, is this group doing differently? I'm creating videos right now. I have this hope that these videos will make a difference. So I'll be looking to see, does this most recent set of samples that has these videos as a support, are they doing and behaving differently than my prior overall population measures as a whole? And if I see enough samples from here on out that are different, if we think back to that control line chart, I would expect to see the overall averages increasing, and I would say it's now time to recalculate the population measures because something different has happened. The population's changed a little bit. We still overall keep these same sets of ideas. We still have to have normal data, but now we're focused on particularly this idea that we would like to compare and contrast some sample measures with the populations. So the idea that we're moving forward to is that instead of comparing a single data value to the population, we might like to compare a sample to the population. And that gets very interesting. I want to make sure that we use the same terminology here for our books, and you'll see me referencing this just a little bit. But as a reminder, for statistics, we have average, and we write that as x bar. For parameters, we have average, and we write that as mu. For statistics, we have variation of s squared. For parameters, we have variation of sigma squared. Sigma for standard deviation, little s for standard deviation, sigma for parameter standard deviation. Sample versus population, statistic versus parameter. You can remember that because statistics and sample both start with the letter S, and population and parameter both start with the letter P. And also keep in mind our convention that parameters and population on the right there are going to involve lowercase Greek letters and capital Latin letters, whereas statistics and samples will involve lowercase Latin letters. I think that's probably about right. Maybe eventually we'll talk about p hat and p for percent. Probability, we've already seen that with our binomial discussions. P hat's going to be the sample calculation of those probabilities. P bar, P hat. depending on your notation. This one is always for the sample calculations, the rough estimate. That's one of the things that we're looking towards. Once we have these measures are specific numbers, and if we think back to this idea of measures of central tendency, we'd say these are point estimators for the sample or the population that gives us a single number to try to describe what's going on. And these also are single numbers that try to describe to us something about the turbulence, the variance, the deviation that we've got in these measures. So once we've got these calculated numbers, from there we start trying to do something with them, trying to get a sense of what's happening. Back in a previous section we cared about central tendency. Now we might care about comparing all these things together and try to figure out a percentile score, some kind of percent to the left and the right. As maybe we looked at with a website, number of clicks. Can we decide how many new customers we're likely to expect on a given day? But now, what we're interested in particular, is taking all of this stuff and starting to imagine what we can do with it. We go away from descriptive statistics, which is, let's say, a histogram or Pearson's index that decides whether something's normal or not and just describes, and we start getting ready to make decisions. We call this inferential statistics. The goal in general with inferential statistics is to take a sample measure, a sample statistic, and project that onto the population with some level of accuracy. Try to come up with something to do with a parameter. There's three general types of inferences that we talk about in this class. Now, maybe it's a chance for a quick English lesson. If I say, let's say, what should I say? Let's say this. You should study hard for your exam. Let me sort of narrow my eyes and look at you. I have just implied that the exam might be challenging and that you should, well, I've just explicitly said that you should study for it, but I've implied that the exam might be challenging, and maybe if I've done that specific look at you, possibly that's enough to kind of hint that something should be going on there. Maybe you should study more than you've been doing. I looked at a particular student and said that. On the other hand, if I look at this from a student perspective, and I've just seen my professor stare me down and say, you should be studying for that exam, I, as a student, make an inference. I decide, you know what, I should probably study more, and in particular, he's suggesting that it's going to be challenging. So imply is sort of the thing I do, and infer is the thing that someone receives. That's that direction there. So when we talk about inferential statistics, what we're doing is we're looking at statistics, namely sample data, and we're trying to receive some bigger piece of information from them beyond what they explicitly say. Maybe my English example isn't all that great because I'm not a great English person. But I don't practice enough. This idea of inference, and in particular statistical inference, is exactly this idea that we're going to look at sample data and then we're going to see something that isn't explicitly stated, but we can still understand what it means about the bigger parametric population data. All right. So we tend to talk about three specific types. There's no magic order that we can write these in. I will kind of keep with our current text here. We have estimation, and then we have testing, and then we also have, I think, generally we call it regression for this book, and then we pretend like we can stop. So these three types of inferences involve estimation, where our goal is to take a piece of the sample value and say, what does the parameter have to look like? If I know x bar, what do I know about mu? And we don't usually have a specific answer, but we probably have a little bit of a range. We also care to talk about testing. We're trying to come up with a decision. And we'll break further into that in some of the next sections that we go on to, some of the next chapters. But the idea is going to be given current sample is something different happening. And I've suggested a use for testing just 10 minutes ago, maybe 5 minutes ago, I guess, when I said, I've introduced these videos as a new aspect of my lecture, and I'm curious, does the new samples, the students this term, behave differently than the population in the past? And for testing, my question would be, have the videos made a difference? Or has one of the new methods that I've introduced this term made a difference in learning? I hope it does, but I don't know yet until I test it. So this is another type of inference because I don't have access to the population of all students in the future who have my videos. I only have access to all students in the past population, plus I have this current set of students, your sample data. And so we can use that sample to try to infer something and try to come to some conclusions about the future as a whole. And finally, we have this idea of regression, and this is that idea that we're going to somehow be able to make a prediction. Based on these videos and based on this current semester's term samples, I have this hope that maybe I can make a prediction about future classes and future students. So, let's take a look at how we can try to access some of this data. What we have over here is a list of numbers, and these list of numbers are for the upper number, I think it's systolic blood pressure. I've organized these in order. This is a pseudo-random sample. It's not quite. I picked it rather carefully. But I can tell you that in general, not for this list of numbers because this is only a sample, but in general, the average blood pressure, the mean blood pressure for the population as a whole is supposed to be about 120 for that upper number. And roughly, this can change a little bit, but roughly the deviation is about 13. So you have 120 plus or minus 13 seems to be your usual deviation. One standard deviation there. Our goal is to take this list of numbers and come up with some interesting calculations for it. In particular, what we would like to do is we would like to talk a little bit about what we call a sampling distribution. This is a sample, if you will. It's not everybody who's ever had blood pressure. There's not enough people up there for that. But the idea of a sampling distribution is this. What if we highlighted these two pieces? And this isn't entirely the way I would normally do it, because of course we have this idea that random selection of stuff's better, and I clearly haven't randomly selected it, because for simplicity's sake, I've organized these in order. But each of these samples that I've boxed, we could calculate the average for them. Now you could plug it into your calculator. Remember, we've got our TI-36X Pro, and we can successfully take that and type in some things into the different columns and see how that's going. I've already got it coded up on Excel. So let me go over here and make sure my Excel file is up, and we can talk about some of these averages. However, as we're doing this, you can definitely be looking at that, and maybe while I'm getting this up in Excel, you should be typing that into your TI-36X Pro. And what we have here for Excel is some numbers. And in particular, I've got these numbers. If I take the average for the first piece, we might call that X bar 1. It's the amount for the first sample, and I am getting 106. And then for the second piece, I'm getting an average of 141.3. And here is the idea of what we call sampling distributions. It's the probability distribution of a simple statistic. And the idea is that we grab each of these pieces and we start to look at them in collections. Notice we've grabbed the same size on each of them. Each of these is size 10. Notice we could have grabbed some different boxes, and we would get different ones. We could take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I could draw my boxes this way, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then of course this way. And if we added them up that way, we would get ourselves a different sampling distribution. The key thing is that there was 20 total in the group, and I took each of them 10 at a time. Or I could take them 5 at a time, and we could have 4 and do top line, middle line, lower and middle line, and bottom line. Or we could do 5 at a time and do these 5 and then these 5 and so on. The idea of a sampling distribution is that you grab your pieces out of the pile in common groups of numbers. So we pick always 10, or always 5, or always 6. And depending on the problem, you might choose to pick different ones. I think in your textbook you have a one where they grab them 5 at a time because there's some fish of some sort and they're having children. I can only take 5 fish from the pond. The idea is this. If you notice, in the way we divided it up first with the top 2 rows and the bottom 2 rows, we had our average for each of the groups. And of course, since we organized this, since I sorted it from low to high, the average for the first thing is lower and the average for the second one is higher. Here's the idea of this sampling distribution. The idea is that if you look carefully, if you were to type in all these numbers into one big collection, from 90 all the way up to 178, add all 20 of them together, divide by 20, you would get yourself the X bar for the whole group. And if we took the X bar for the whole group, Excel has already told me that that's going to be 123.65. In fact, you should probably pause me for a second and verify that, either on your calculator or in Excel. And here's what I want you to notice, and this is for the all 20. I'll put a little subscript 20 there. I know for the population as a whole that I expect an average of 120. If I grab just some single groups of 10, maybe I have a sample average of 106 or a sample average of 141.3. But notice when I got the total sample average for all 20, that we were able to have 123.65. That was a lot closer to the population number than anything else we've done. The idea is that we can successfully, as we get a larger sample size, expect the sample calculations to become closer to the real population calculation. And that's what we mean when we talk about inferences and doing this as an estimation. The sample value as a whole should look very similar to the population once we have enough. Enough for us usually means around 30, with any luck. Now, that of course depends on how normal your data is. So let's talk about how normal our data is. If this was a true random sample where I'd gone across some country or across the world even and just grabbed 20 people at random, I would expect this to fit the normal distribution. We can check with the Pearson's index. You take 3 times X bar for the whole group, that's 123.65, minus the median. You can break this guy in half and say, okay, the half's right here, 120, and divide it by the sample standard deviation. Calculate sample standard deviation. If you've entered all 20 of these points in your calculator, you can just look for S. If you do that calculation, I've already had Excel do that for us, and I got the number of 0.46. Again, pause me, go calculate that out, and see that you get the same number. We got it by adding all these numbers together. That gave us X bar, which should be this. The median, which should be the numbers in the middle. We have an even number, so we'll take 120 plus 120 and add them together and divide by 2 and get 120. And then multiply by 3, and then divide by the sample deviation. And the sample deviation for us is going to be a number that's close-ish to 23 or 24. I didn't calculate that out yet. But if you calculate that, you can find your number here. And if you get that, you should get 0.46, roughly. I rounded to a couple decimal places. That number lives between -1 and 1, and so Pearson says this is not skewed, namely this is a normal sample, and it's a random sample because I said so, and so this is a pretty good list of things to look at, and because it's a pretty good list of things to look at, we see that overall as a sample, if we grab all these numbers, because it's not skewed, this is very close to what we'd expect the population to do, with notice just a little bit of error. So what are we trying to do from here? Well, our goal with this estimation business is to try to get ourselves ready for figuring out if I just have sample data, what's the population doing? You see, in the case of blood pressure, we're unnaturally lucky. We happen to actually know what the population does because just about every time I go to any medical environment, they take my blood pressure. In fact, blood pressure is so common, you can even get your blood pressure measured at most drugstores. There's going to be a little machine you can stick your arm in. You can even buy one pretty cheap and take it home. I think there's even a watch that does it now. So we actually have the ability to cheaply and easily access population information, which makes this a good example to look at because we can see it from both points of view, right? But if we didn't have access to the population, let's say we had no real easy way to measure blood pressure, it was expensive to collect the data, we'd never know that it was 120 overall. But look, just by doing it 20 times, not the 7-something billion times that its current blood pressure is on Earth because of the number of people we've got, but just by doing it 20 times, we get a number that's very, very close to what it really should be. And that's the power of a purely random sample grabbed from a normal distribution of data. You don't need all that many samples to understand how everybody works. And that's where we're going. Now notice a couple other things. Depending on how we try to take subsamples, really, of our 20-person sample, if we grab it in groups of 10, we could get ourselves some different sample collections. We could have this group of the sample and that group of the sample. And again, think of it this semester. I have my overall population of all my statistics students ever. I want to figure out how that works. But I don't have access to all my statistics students ever because some of them are in the past, and I probably have those numbers, but hopefully a lot of them are in the future, and I can't grab those people yet. I can grab this semester's worth of information, and I have students both online and face-to-face. Altogether, you make a current sample of students, but maybe it makes sense to have the face-to-face students as well as the online students. And so we can sort those into a couple different categories. But the idea is if I add the face-to-face average together with the online average, that should be the total average of all my students this semester. That should be this. And notice something clever. If you've gone to all the work of typing in all 20 of these numbers into your calculator, you'll find that the sample mean for all 20 is 123.65. If then maybe in list 2 and list 3 you had typed in this group and this group, you would find that those list averages were 106 and 141.3. But look at something cool. If I take 106 plus 141.3 and divide that number by 2, I get 123.65. The average of the averages is the same as the average of all the data points together. That's big. The average of the averages, the average of the subsample means, is going to be the same as if we had added up all the pieces individually. That's one thing to notice. There's another thing to notice about this data. Notice that this first 2 rows tends to be a little lower than what we happen to know blood pressure really is. This is a bit of a deep thought that we're going for here. If I just grab one single thing at random, I'm going to try to not look and I'm just going to put my hand down. I picked a single blood pressure of 150. Now, if you know anything about blood pressure, that's not so hot. If you go out on the street, jump a person, and take their blood pressure, you might find that for one single person, the blood pressure was quite high. Probably particularly if you jumped them, because that would get the adrenaline going, right? However, even if you're in the business of jumping people on the street, scaring them, and taking their blood pressure, so you're in this high category of blood pressure people, any one particular person you grab might have a rather high blood pressure, and you might be tempted to say, you know what, blood pressure is kind of high in general. However, notice something about even the high sample average. One person that we grabbed at random, 150. But if we grab 10 of them together, the average for that was 141.3. Much closer to the 120 than the 150 is. by like what, 9.7? The more people you have in your group, the more your group starts to behave normally. One person by themselves can be very abnormal. There's a 30-point difference here. But if we get enough people in a group, even if they're kind of high overall, we start to see the property of the group. It reins in the extreme parts, and you come together. We know that this works in things besides statistics. If you get a committee of people together and sit them around a table, you'll eventually find that any single member of the committee might have had very strange radical ideas, but they eventually come together. Now, if you've taken a psychology class, you know there's a risk to this. It's called groupthink, and suddenly no individual has any clever new ideas, and everyone just kind of agrees on the same stuff. And that can be bad. But in the case of trying to measure how a population as a whole works, it can be a very good thing. Furthermore, if you have one sample's average and you can find another sample, you can take those averages together and you start to get even closer to what the population's doing. The more measurements you take, the better you are at being able to infer this very interesting estimate of what the population's doing. And whether you measure them up all one at a time, using this formula, or whether you add them up in groups and take these guys and average the averages, it's going to be the same thing. So you'll find, if you're looking in your book, that they write down a very interesting fact, namely, let me make sure I use the exact same notation we're using here. If you were to find the population average of all the sample averages, if you were to grab the pieces and average these, that's the same thing as if you just counted all the pieces one at a time and found the whole collection. This is an aspect that is essentially called the central limit theorem. And it says that once you get enough samples, if you average the averages, that's the same thing as averaging all the individual pieces. It's a very interesting idea. Now, the central limit theorem doesn't quite say that. It's going to go a little bit further. But that's the idea of this central limit theorem that we're trying to get ready for. For this estimation process, the average of the averages is the same as the average of all the data points inside those averages. It doesn't matter how you split up your numbers. If you have some of those pieces averaged and then average the averages, or whether you add them all up together, you're going to come to the same final spot. That's very powerful. So let's look at that in context of a slightly more interesting problem. We can get some erasing here so that we can fit this up. I'm going to keep these same numbers on the left. We're going to focus on this estimation business. We're going to compare and contrast some things. Our old z-score compared a single data point to the group as a whole. And if we compared a single data point, taken at random, like 150, and compared it to the group as a whole, we could calculate out the z-score for that, yes? And I have 150 minus 120 divided by 13. Since we do happen to have the population stuff that I'm giving you. I'm getting 2.31. I'll write this wiggly equals sign because I got 2.30769 and I'm rounding it to 2 decimal places. We could look that up on our z-score chart for areas of standard normal deviation, and we could find that a blood pressure of a top score of 150 on our raw score, once we convert to z-scores, is a score of 2.31. And if you go down to 2.3 on your column here, go down to 2.3 and go across to 0.01, we get 0.9896. Which is quite a lot of shading over here to the left. 98.96% of people have a blood pressure lower than this person. We grabbed a single person at random off the street, and maybe their blood pressure is quite different from normal. was pretty hard really to find this person if we look at the world as a whole, but it's entirely doable. In this particular sample, there was a 1 out of 20 chance that I would find someone who was 98.96% more blood pressure-y, if I can invent that word, hypertensive maybe, than anyone else. So think about that. If I've grabbed a perfect normal random sample, one piece of person from there, well, that chance is just 1 out of 20, thinking back to chapter 4. And yet, that 1 out of 20 chance person was very, very different from almost everyone else in the world. So it was very likely, if you just have 20 people in your sample, that you'll have someone who's rather odd. However, if we then were to grab this category of people, and again this is a rather strange one because I haven't picked them at random, let's recalculate that. It would be interesting to figure out a z-score for this group. But we have to change our z-score formula just a little bit, because we wouldn't be talking about comparing a single x to the population. Instead, we would want to compare a sample to the population of samples. If we were writing our z-score out, we wouldn't have x anymore, we'd have x bars. And we wouldn't be having the average of all the single pieces, we want to talk about the population of all the samples. We call that mu with the subscript x bar. And we're not dividing by the standard deviation of one piece, we need to divide by the standard deviation of the samples. So it's sigma x bar. Don't let the notation here confuse you. We're not doing something crazy. We're just saying, here's all of our data in our sample, and we're picking it out with these little subsample pieces. So we want to find the average of all the pieces for the population, and the average deviation if we grab things in chunks rather than one at a time. But I haven't ever used these terms before, so I have to give you the formula for them. However, I just said mu x bar equals mu, and we saw it because if I take these two and add them together, they'll equal the average of everything. The average of the averages is the same as the average of all the individual pieces. So when I write this, I don't really have to write that. I can write what he's equal to, which is the normal mean that we're used to, because it doesn't matter how you organize things when you're adding them all up and dividing by the total number. If you add them up in chunks, or if you add them up one at a time, you're going to get to the same spot. The one piece I do have to give a slightly different term for is this piece right here. We have to take this idea of standard deviation and we have to recalibrate it for the number of groups we've got. And we do that like so. We not have a big zero looking thing here. Sigma, the normal sigma for all the individual pieces, divided by the square root of little n being the number of things in this sample. This is a new z-score. Just like we had introduced a sample and a population mu and mean, so too, now we start to introduce some new z-scores. This z-score compares a single point to the population. This z-score compares a sample to the population. We've seen that if you compare a single point to the population, you can get a single point that's quite out of the ordinary. But if we compare a sample to the population, like I might want to do with this term's classes, to my old classes, if I hope this video is helping, then we're going to want to be plugging into this formula. So you have to be careful when you read a problem or when you come up with something in the real world to decide, what are you trying to do? It's the difference between saying, if I have a patient come in off the street and I want to decide, is this patient hypertensive? Well, that's one person that I'd like to compare to the population as a whole. And then I can make a decision. If it was this person, I would say, yes, get this person some medicine, stat. On the other hand, if I'm trying to ask the problem of, does this town have people who overall have higher blood pressure than they should. Well, now I want to compare the sample of the town to the population as a whole. And we're no longer comparing one person at a time, we're comparing a group. When you compare a group, you have to have a point estimator for that group, and we call that the group mean. So you've got a sample statistic that you're comparing and contrasting with the population parameters, and it still can give us a z-score so that we can still go back to the normal distribution curve and find out how unreasonable was this sample, how like everyone else was it, what are the percents. This is an absolutely vital idea, and it's the whole point of everything going on from here. I see today, this very lesson right here, as a real turning point between just the simple stuff that we did before where we were just trying to describe statistics and do descriptive statistics, and everything after today is going to be about inferential stats, trying to understand how either a single person or a group of people in a sample compares to the population. If we happen to be lucky enough to know population data, we can calculate a z-score. If we are not lucky enough to know population data, then we're only going to be able to use the sample stuff as an estimate. And that will be what we pretty much do the whole last half of this course. So let's go ahead and plug these numbers in. If we grabbed this group, these bottom 10, we would have 141.3 minus the population measure of 120, divided by sigma, which is 13 for blood pressure, divided by square root of 10. Square root of 10 because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things that built up this group of people. Again, our calculators can calculate this out. And again, maybe I tend to like to pop in this fraction bar here, and then we can have 141.3 minus 120. On the bottom of the fraction bar, I can hit the fraction bar another time, and on the top I can write 13, and on the bottom of that I can write second and square root and 10. I can scroll over to the side and hit enter, and it'll give me a number, in this case 5.18. If you look it up in your chart, for z values bigger than 3.49, use 1 to approximate the area. This all this area to the left we say is 1. This is extraordinarily unlikely to happen. This guy, the person with a blood pressure of 150, grabbing one person with a blood pressure of 150, there are 98.9% of people are going to have lower blood pressure than this person. So he's pretty difficult to find, really. It'd be rather challenging to find such a person overall, you would think. To find a group of people, to find a group of 10 people at random who had an average blood pressure of 141.3, that's essentially never going to happen. This is an extraordinarily high z-score. It's insane. This is the big idea. It's simple enough to find one person who does something out of the ordinary. That's not complicated. At random. You're just picking things at random. But notice, I didn't pick this second group at random. I, in fact, explicitly organized it from low to high, and we focused in on this bottom group directly. And that gave me the 141.3. If you have a random grabbing, you don't expect all the people to be higher than average. You would expect some above and some below, like we have for the overall sample of 20, right? On the here we've got the low ones, and here we've got the high ones. Once you get even just 10 people in a sample, the idea that the sample is going to be so far different from what you know the population does as a whole becomes extraordinarily unlikely. What does this tell me? It tells me that one person might behave differently than the population. It can happen. It's expected. But a group of 10 starts to get a lot more close to what the population in general does. It becomes much more unlikely that they're going to stretch too far away from what the population would be doing. A group of 20, even less so. And we even saw it once we took all 20 in here. If they were grabbed randomly, this 123 was very close to the 120. And this makes this a rather confusing lesson because of all the things you have to keep in your head. So let me take a moment here to try to summarize this, and I do apologize because I think I'm going to probably go over my normal 40 minutes. One person that you grab at random might be average, might be above, might be below. We can calculate that, comparing one person to the population. But once you get a group of people, you expect that group to engage in a process that we call normalizing. If you've randomly selected the people in your group, you would expect it to be very odd for the group to be so different from the average. Notice, one person with a score of 150 above 120, that was still possible. Likely? No. There's only 2% or so of people who are higher than, I guess, 1%, but it still could happen. Finding a group of 10 people at random with a blood pressure average this high, if you truly did it at random, very unlikely. Now, of course, we happen to know that the United States has a hypertension epidemic, and in particular, if you're thinking in a hospital setting, well, maybe people are already in there because they have high blood pressure. Remember, patients walking in off the street complaining of high blood pressure are not selected at random. I'm talking about a truly worldwide random sample selection here. Groups start to cohese to the middle, and it's that idea that is the section that's called central limit theorem. So let me give an explicit mention of what the central limit theorem sort of says. What it says is this. The central limit theorem tells us that if we have a distribution, then the sample mean based on a random sample will start to approach the group as a whole. It'll start to tighten in. And we saw that here. One person might be high. The whole group as a whole starts to get very close. You start to have this cohesion. It's very similar to the probability idea of the law of large numbers. You start to have this cohesion where things get into play. And you say, well, once we've done enough, we expect them to start behaving according to the theory. This leads us to a lot of possibilities. What does it say? It says that I don't need to have a whole population to get close. I can talk to 20 or 50 people, and I'm probably almost just as good as talking to the entire population, as long as I pick them perfectly at random. Now we know from some of the first chapters that we've looked at in this book how difficult it is to get a truly random sample, because you have these confounding variables, right? You could go out and have a random sample attempt, but you walk up and knock on someone's door at random, and they tell you they don't want to speak to you. Well, now that's no longer a random sample because some people have chosen to not talk. Think about, so the U.S. Census maybe is a good example of something that is a pretty good random sample because by law you have to answer and they'll come and find you and hunt you down if you don't answer until you do answer. It makes it a much better random sample. Most surveys that we do tend to be having this idea that, well, we would like to get a random sample, and you've seen that 20 is probably really almost good enough if it's a perfect random sample. For at least blood pressure, it seemed to work well. However, you might want to have 50 or 200 or even 3,000 or 4,000 if you don't have a perfect random sample. So if you look at political surveys, if people are trying to figure out who's going to vote for which president, you'll find that most news organizations in the United States have 2,700 people or so that they tend to try to telephone because they know some of them are going to say no, and it's their hope that overall some people will hang up the phone, but with 2,700 people in sample, enough people will pick up the phone and answer the questions that they can somehow get this to work. So, central limit theorem, we have a new z-score, and we're going to have to now decide when we read problems, are we comparing a single point to the population, or are we comparing a sample to the population? Either way, you plug it into the z-score, and once you get the z-score, you look it up in the same chart. So take a look at the suggested problems for these sections on my website and look into this, practice, take a look at the homework, because of course we do have a midterm coming up, and I can guarantee you that z-score and sample z-score are going to be a big part of this. I will see you in just a few minutes for me, but of course for you it will be in the next lesson for the last part in this section. But until then, be safe.